Hello. Let's study the topic of single phase AC transformers. A transformer is an AC device used to change a high voltage low current AC into a low voltage high current AC and vice versa without changing the frequency. Thus, it just transfers electrical power from one circuit to another circuit, which is without changing frequency. Constructionally, it can be shell type or core type. In case of shell type transformers, the windings, which are low voltage and high voltage, those are wrapped around the center leg of laminated core. And in case of core type, the windings are wrapped around the two sides of laminated square core. The core is nothing but some iron core which is being provided for the flow of flux being generated. So a single phase transformer is nothing but an AC circuit, which is a static device where to one of the windings or one of the circuits known as primary we apply voltage V1 AC quantity, because of which current I1 flows through it. Flux phi is generated. That flux flows in the iron core. Then, according to law of electromagnetic induction, EMF E1 is generated in primary circuit itself. Because of Lenz's law, the direction of V1 and E1 is opposite to each other. Usually, primary side has number of turns equal to N1. Now, the same core is associated with secondary circuit also. Secondary circuit consists of same copper or another conductor winding which is having number of turns N2. Same flux phi is associated with secondary winding also, because of which EMF E2 is generated. Because of EMF E2, current I2 flows through it, and thus load which is connected at secondary which experiences voltage V2. Thus, a single phase transformer or any transformer works on the principle of mutual inductance. In case of ideal transformers, there are special characteristics, one of which is zero leakage flux. Windings are assumed to have no resistances. The core in which that flux flows has infinite permeability, and obviously that core is lossless. So this is the representation of ideal transformer. We can see conceptually current V1 leads current I1 by 90 degree. Current I1 is obviously in the direction of flux phi. So we can say that V1 leads phi by 90 degree. Direction of V1 and E1 is opposite to each other, but E2 and E1, they are always in same direction. So we can say that magnetization current, which is nothing but current I1, it leads E1 by 90 degree, that is phi also. Now when no load is connected at secondary, let's have some phasor diagram. We have already seen it in previous slides. Current I0 is nothing but combination of current IC and IM. IM is nothing but magnetization current which is used to create flux phi, and IC is nothing but current which flows through copper winding, and because of which I square R losses occur. So I0 is nothing but phasor representation of IC and IM. This is the diagram when no load is connected. See again, when no load, okay, this is the transformer on load, assuming no voltage drop in the winding, similar to that. Now see, when load is connected, main load is connected, it has these phasor diagrams depending on various power factor. This is the diagram, rather phasor diagram, when unity power factor load is connected, that is resistive load. This is when lagging power factor, and this is for leading power factor on load. Now there are different tests performed for a transformer. These tests are nothing but to experience or check the performance of transformer, one of which is open circuit test of a transformer. As we can see from the diagram, in case of open circuit, we apply rated voltage and rated current flows through the transformer primary side. We measure that voltage, power and current which is being flown through primary circuit. Secondary circuit is obviously kept open, so ideally no current should flow through secondary circuit because secondary circuit is open. Now as we know, V1 I1 is equal to V2 I2. As I2 is 0, V1 I1 should be 0. That means no current should flow through primary also. But it does not happen. A very small amount of current flows through primary circuit. A small amount of current flows through primary circuit which is used to generate voltage E2 because of flux phi. So ideal use of that current I1 is to generate flux. So it is assumed that I square R or resistive losses are assumed to be very negligible in case of open circuit test. So thus we can say that open circuit test is used to calculate core losses or iron losses. Whereas in case of short circuit test, the two ends of secondary windings are shorted and rated current is assumed to flow through secondary side. So very small or negligible amount of voltage is applied at primary, because of which rated current flows through it. For the flow of rated current through secondary, very small amount of secondary voltage is needed to be generated, and it is assumed that all the energy power which is being supplied is used to generate copper losses I square into R, because that amount is huge. So open circuit test gives us core losses, short circuit test gives us copper losses. Now there are two different parameters again, voltage regulation and efficiency. The output voltage of a transformer varies with load even if the input remains constant, because a real transformer has series impedances within it. Full load voltage regulation is a quantity that compares the output voltage at no load with the output voltage at full load. So regulation is nothing but So equations are given in regulations. So voltage regulation is nothing but no load voltage minus full load voltage upon no load voltage. Efficiency is nothing but power output delivered to the secondary and supplied, that is input power, multiplied by 100. Now input power is nothing but output power plus losses. So we can have efficiency is equal to V2 I2 cos phi upon copper losses plus core losses plus V2 I2 cos phi, that is kVA rating. As I discussed earlier, there are two different types of losses. One is core loss, another one is copper loss. Core loss consists of hysteresis and eddy current loss. Copper losses are I square into R for primary as well as secondary. Copper losses are always constant in nature. Variable losses are, sorry, iron losses are always constant and variable losses are copper losses. It can be seen from this equation or derivation that condition for maximum efficiency is copper losses have to be equal to iron losses. So variable losses and core losses, when they come in equal amount, at that time maximum efficiency can be achieved. And this is the condition for load at which maximum efficiency can be achieved, which is nothing but full load kVA rating into square root of ratio of iron loss and full load copper loss. Okay. So these are few points which we just discussed about transformers, single phase AC transformers. Thank you.